Welcome to this Maths Made Easy video on equations involving exponentials. To start with, let's take a look at using a calculator. Now your calculator will have several buttons to do with logarithms. If we have a button that looks like this, so this is log, and we have a square underneath here, and a square here, okay? Well, this bottom box here allows you to do the base, and the box on the right is the logarithm that we're taking. And this button here allows you to do any logarithm. If we have a button that looks like this, so log with base 10, and then a box here, this is for logarithms base 10 only, okay? And if you see a button that says ln, this is for the natural logarithm, which we will see later on in the course. So for example, if we want to do log 81 base 4, then using our calculator, we would enter 4 into our base here. We would put 81 into this box here, and we would press the equal symbol here, okay, or enter. And that would give you your value here. So that gives us everything we need there for using a calculator. Moving on now, take a look at exponential equations. Now some exponential equations look rather complicated, but they are usually just quadratics in disguise. And they take the form AP to the 2x plus BP to the x plus c equals 0. And we solve these by substituting y equals p to the x. So letting y equal to p to the x, and noticing that y squared is equal to p to the 2x, okay? And that gives us a simple quadratic, ay squared plus by plus c equals 0. And this gives us two roots, y equals r1 and y equals r2. And putting x back in gives p to the x equals r1 and p to the x equals r2, which are two equations that we already know how to solve. So for example here, we've got 3 times 6 to the 2x minus 7 times 6 to the x plus 2. And this is all equal to 0, and we want to solve for x here. So how would we do this? Well, we notice this is just a disguised quadratic. This is 3 times 6 to the x all squared minus 7 times 6 to the x, so minus 7 times 6 to the x, and finally plus 2 here. And this is all equal to 0. So therefore, if y is equal to 6 to the x, what we've got here is 3y squared minus 7y plus 2 equals 0. And the first thing we always want to check here is whether we can factorise our quadratic. And in this case, we can factorise. What we get here is 3y minus 1 times by y minus 2. And this is all equal to 0. So in that case, what we get now is 3y minus 1 equals 0, so therefore 3y is equal to 1, which tells us y is equal to a third. What we've also got here is y equals 2. Now remember, we're not solving here for y, we're actually looking for x. So we need to replace now y with 6 to the x. That's the substitution that we originally used. So if we just finish this now with a different colour, just highlight this, what we've got now is 6 to the x equals a third. We've also got 6 to the x is equal to 2. So in that case then, what we've got now is x is equal to the log of a third base 6, or x is equal to log of 2 base 6, okay? And all we need to do now is just simply evaluate both of these on our calculator. And if we do this correctly, we get minus 0.613, and that's one value of x here, so x is equal to minus 0.613, or x equals 0.387 there. Okay, so that gives us the solution to our example, and gives us everything we need for exponential equations. Moving on now to take a look at logarithm equations. So difficult logarithm equations often require you to use more than one law of logarithms. Now if we take a look at this example here, we can see this in action. So here we have log of 21x minus 2 base 3 minus 2 log x base 3 is equal to 3. So the first thing I'm going to do here is notice we have this minus 2 in front of the logarithm, so we can apply the power rule here. We can take this minus 2 as a power here for this x. Okay, so this would become a plus here. So if we rewrite this, this becomes log of 21x minus 2. Okay, that's still base 3. This becomes a plus now. We're taking the minus 2 as the power here for the x. So this becomes plus log x to the minus 2. Okay, so that minus 2 has gone as the power there for the x. And again, this is base 3. So this is all equal to 3 now. Now if we notice here, we have the summation here, the addition of two logarithms. So in that case, as they have the same base, we can write this as a single logarithm. And in that case then, writing this as a single logarithm, we get log. And remember, combining these as a single logarithm, this becomes the product. So we get 21x. So this is 21x minus 2 times x to the minus 2. Okay, and don't forget our base here, base 3. Okay, and this is still all equal to 3. Now here, what we want to do is get rid of this logarithm here, base 3. So to do that, we anti-log. So in that case, taking the inverse here, we're going to get 21x minus 2 times by 1 over x squared here. This is x to the minus 2, which we could write as 1 over x squared. Okay, so we times that by 1 over x squared. And this is equal now to 3 to the power of 3 there. Okay. Simplifying this then, what we get here is 21x minus 2 over x squared. Okay. Just writing this then as a over the denominator here of x squared. And this is equal to 3 cubed. And 3 cubed is just simply 27. So here now what we want to do is solve for x. So the first thing I can do is multiply the left hand side and the right hand side of this equation by x squared. So if we do that up here, what I get then is 27x squared is equal to 21x minus 2. Okay, so here now, I'm going to set this equal to 0. So in that case, we need to minus 21x and add 2 to both sides. And if we do that here correctly, what we get then is 27x squared minus 21x plus 2 is equal to 0. Okay, and in this case now we have a quadratic which we can hopefully factorize, but if not, we would just use a quadratic equation, for example. But what we find here is this does indeed factorize, and what we obtain is 9x minus 1 times by 3x minus 2 there. Okay, and this is all equal to 0. So here now we obtain two solutions. One of the solutions is when 9x minus 1 is equal to 0. So that gives us 9x equal to 1. And in that case, x is equal to 1 over 9. Okay, so x is equal to 1 over 9. And our other solution here, we obtain when 3x minus 2 is equal to 0. So that means 3x is equal to 2. And in that case, x is equal to 2 over 3 there. Okay, so that gives us the solution there to that example, and that gives us everything we need for logarithm equations. And finally, let's take a look then at real life problems. Now, exponentials and logarithms appear frequently in real life. An important skill is being able to solve real world problems involving exponentials and logarithms. So if we take a look at this example here, which is an application of real life problems. So we're told a car depreciates in value over the course of several years according to the function given here, which is v equals. Okay, we're told v is the value of the car and t is the time in years. And there's 3 parts to this example here, part 1, part 2 and part 3. So let's start with part 1 here. Now we're asked how much is the car when it's brand new essentially. So in that case, that would be when t is equal to 0. The time in years is just simply 0. So t equals 0, and all we do now is we take our equation for v here and substitute t equals 0 in. Okay, so therefore v is going to be equal to 14,000 times 0.9 to the power of 0. Okay, and remember anything to the power of 0 here is equal to 1. So that gives us 14,000 times 1, which is equal to 14,000. Okay, so that's our first part there, hopefully nice and straightforward. For the second part here, we're told John has owned his car for 9 years. How much is it worth in value? So here we just know this. So we know that he's owned the car for 9 years. So what that tells us then is that t is equal to 9. And again, all we simply do here is substitute t equals 9 into our equation for v. So therefore, v here is equal to 14,000 times 0.9 to the power of 9 there. And if we evaluate this on our calculator, what we find here is this is equal to 5,424 there. Okay, so that gives us the solution to the second part of this example. And finally then, the third part here, we're told Clarissa buys a new car today. How many years until it is worth half of what she paid? So, this is definitely the trickiest part of this example. The first thing to note here is the new cost of the car, and we established that in part 1 here, okay? So the new price, or the new value here, is 14,000. So in that case, what we're looking for is half of that value. So half of 14,000 is 7,000. So half here is equal to 7,000. So that's the first thing we need to know here. So we're looking for how many years until it's worth this in value. So in that case, we need to use the fact that v is equal to 7,000 and then solve our equation here for t. So what would that look like? Well, in that case, we're saying 7,000 is equal to 14,000 times 0.9 to the power of t there. Okay, and now we're just going to solve for t here. So in that case, we can divide both sides of this equation by 14,000. So remember, we're just looking for 0.9 to the power of t and then to just find t. So in that case, we get 7,000 over 14,000 is equal to 0.9 to the power of t here. And clearly 7,000 over 14,000 is just a half. So therefore, what we can say here is 0.9 to the power of t is equal to a half. And finally, we're just looking for t here now. That would tell us how many years it is until it's worth half of what she paid. And clearly to find t now, we just need to use logarithms. So in that case, t here is going to be equal to log of a half, with our base being this 0.9 here. Okay, so log of a half base 0.9. And here now we just evaluate this on our calculator, and what we find then is this is 6.58. Okay, so that gives us the value then for t, and that's what we were looking for there. So that gives us the solution to that example there for all 3 parts, and that gives us everything we need for real life problems. And that concludes this Maths Made Easy video on equations involving exponentials.